Welcome back. In this session, we will be taking a closer look at the science and engineering practices. The goals are understand the science and engineering practices, to be able to identify the practice and a performance expectation, recognize the important role of the practices in science. Engaging in the practices of science helps students understand how scientific knowledge develops. This direct involvement gives them an appreciation of the wide range of approaches that are used to investigate, model, and explain the world. Engaging in the practices of engineering also helps students understand the work of engineers, as well as the links between engineering and science. Participation in these practices also helps students form an understanding of the cross-cutting concepts and disciplinary ideas of science and engineering. Additionally, it makes students' knowledge more meaningful and embeds it more deeply into their worldview. The development process of the standards provided insights into science and engineering practices. These insights are shared in the following guiding principles. Students in grades K through 12 should engage in all 8 practices over each grade band. Students' abilities to use the practices grow over time. However, the NGSS only identifies the capabilities students are expected to acquire by the end of each grade band. Practices grow in complexity and sophistication across the grades. The framework suggests how students' abilities to use each of the practices should progress as they mature and engage in science learning. Each practice may reflect science or engineering. Each of the 8 practices can be used in scientific inquiry or engineering design. The best way to ensure a practice is being used for science or engineering is to ask about the goal of the activity. Is the goal to answer a question? If so, students are doing science. Is the purpose to define and solve a problem? If so, students are doing engineering. Practices represent what students are expected to do and are not teaching methods or curriculum. The framework occasionally offers suggestions for instruction, like how a science unit might begin with a scientific investigation, which then leads to the solution of an engineering problem. The NGSS avoids those suggestions since the goal is to describe what students should be able to do rather than how they should be taught. The 8 practices are not separate. They intentionally overlap and interconnect. The 8 practices do not operate alone. They occur sequentially and even overlap. For example, the practice of asking questions may lead to the practice of modeling or planning and carrying out an investigation, which may lead to analyzing and interpreting data. The practice of mathematical and computational thinking may include some aspects of analyzing and interpreting data. Just as it is important for students to carry out each of the individual practices, it's important for them to see the connections among the 8 practices. Performance expectations focus on some but not all capabilities associated with a practice. As the performance expectations were developed, it became clear that it's too much to expect each performance to reflect all components of a given practice. The most appropriate aspect of the practice is identified for each performance expectation. And lastly, engagement in practices is language intensive and requires students to participate in classroom science discourse. The practices offer rich opportunities and demands for language learning while advancing science learning for all students. English language learners, students with disabilities that involve language processing, students with limited literacy development, and students who are speakers of social or regional varieties of English gain much from science learning that involves language-intensive scientific and engineering practices. When supported appropriately, these students are capable of learning science through their emerging language and comprehending and carrying out sophisticated language functions using less than perfect English. By engaging in these practices, they also build on their understanding of science and their language proficiency. The science and engineering practices are based on an analysis of what professional scientists and engineers do. The 8 practices are asking questions and defining problems, developing and using models, planning and carrying out investigations, analyzing and interpreting data, using mathematics and computational thinking, constructing explanations and designing solutions, engaging in argument from evidence, and obtaining, evaluating, and communicating information. The first practice, asking questions and defining problems. A practice of science is to ask and refine questions that lead to descriptions and explanations of how the natural and design world works, and which can be empirically tested. Asking questions is the first step in science and engineering. In science, we ask questions to explain phenomenon, and in engineering, we ask questions to define problems that will lead to designing solutions that will fulfill human needs. Scientific questions are distinguished from other types of questions in that the answers lie in explanations supported by empirical evidence, including evidence gathered by others or through investigation. Engineering begins with defining a problem to solve. However, engineering may also involve asking questions to define a problem, such as what is the need or desire that underlies the problem, what are the criteria for a successful solution. Other questions arise when generating ideas or testing possible solutions, like what are the possible trade-offs, what evidence is necessary to determine which solution is best. As teachers, we can develop strategies that can help students come up with questions on their own, teach them to refine the questions and recognize which ones are good and which ones are science ones, and which questions we can answer through design and science lab. The next practice is developing and using models. A practice of both science and engineering is to use and construct models as helpful tools for representing ideas and explanations. Models are physical, conceptual, clear, external, and shared by everyone. They are an analogy for how phenomena and designs work. They can be structural, behavioral, or functional. Models include diagrams, physical replicas, mathematical representations, analogies, and computer simulations. In science, models are used to represent a system or parts of a system under study to help in the development of questions and explanations, to generate data that can be used to make predictions, and to communicate ideas to others. Students can be expected to evaluate and refine models through an iterative cycle of comparing their predictions with the real world and then adjusting them to gain insights into the phenomenon being modeled. Models are based upon evidence. When new evidence is uncovered that the models can't explain, models are modified. In engineering, models can be used to analyze a system to see where or under what condition flaws might develop, or to test possible solutions to a problem. Models can also be used to visualize and refine a design, to communicate a design's failures to others, and as prototypes for testing design performances. Planning and carrying out investigations. Scientific investigations may be done to describe a phenomenon or to test a theory or model for how the world works. The purpose of engineering investigations might be to find out how to fix or improve the functioning of a technological system, or to compare different solutions to see which best solves the problem. Whether students are doing science or engineering, it's always important for them to state the goal of an investigation, predict outcomes, and to plan a course of action that will provide the best evidence to support their conclusions. Students should design investigations that generate data to provide evidence to support claims they make about phenomena. The next practice is analyzing and interpreting data. Once collected, data must be presented in a form that can reveal any patterns and relationships and that allows results to be communicated to others. Because raw data have little meaning, a major practice of scientists is to organize and interpret data through tables, graphs, or statistical analysis. This analysis can bring out the meaning of the data and their relevance so that they may be used as evidence. Engineers, too, make decisions based on evidence that a given design will work. They rarely rely on trial and error. Engineers often analyze a design by creating a model or prototype and collecting extensive data on how it performs, including under extreme conditions. Analysis of this data not only informs design decisions and enables the prediction or assessment of performance, but also helps define or clarify problems, determine cost feasibility, evaluate alternatives, and investigate failures. To get started at the elementary level, teachers can have students use a science notebook for collecting data. It can include drawings, numbers, words, tables, and graphing are a good way to organize data, which will help with analyzing it. The next practice, using mathematics and computational thinking. Although there are differences in how mathematics and computational thinking are applied in science and in engineering, mathematics often brings these two fields together by enabling engineers to apply the mathematical form of scientific theories and by enabling scientists to use powerful information technologies designed by engineers. Both kinds of professionals can accomplish investigations and analyses and build complex models, which might otherwise be out of the question. Students are expected to use mathematics to represent physical variables and their relationships and to make quantitative predictions. Other applications of mathematics in science and engineering include logic, geometry, and at the highest levels, calculus. Computers and digital tools can enhance the power of mathematics by automating calculations, approximating solutions to problems that cannot be calculated precisely, and analyzing large data sets available to identify meaningful patterns. Students are also expected to engage in computational thinking, which involves strategies for organizing and searching data, creating sequences of steps called algorithms, and using and developing new simulations of natural and design systems. Classroom instruction should enhance all of the sciences through the use of quality mathematical and computational thinking. The next practice is constructing explanations and designing solutions. The goal of science is to construct theories that give an explanation of how the world works. Students are expected to construct their own explanations as well as apply standard explanations they learn about from their teachers or reading. An explanation includes a claim that relates how a variable or variables relate to another variable or a set of variables. A claim is often made in response to a question, and in the process of answering the question, scientists often design investigations to generate data. The goal of engineering is to solve problems. Designing solutions to problems is a systematic process that involves defining the problem, then generating solutions, testing, and improving solutions. When students demonstrate their understanding of the results of a scientific idea by creating their own explanations of phenomena, they are engaged in an essential part of the process when conceptual change can occur. Argumentation is a process for reaching agreements about explanations and design solutions. In science, reasoning and argument based on evidence are essential in identifying the best explanation for a natural phenomenon. In engineering, reasoning and argument are needed to identify the best solution to a design problem. Argument in science goes beyond reaching agreements and explanations and design solutions. When they're investigating a phenomenon, testing a design, or constructing a model to provide a mechanism for an explanation, students are expected to use argumentation to listen to, compare, and evaluate competing ideas and methods based on their merits. And our last practice is obtaining evaluation and communicating information. Being able to read, interpret, and produce scientific and technical text is a fundamental practice of science and engineering, as is the ability to communicate clearly and persuasively. Scientists and engineers use multiple sources to obtain information used to evaluate the merit and validity of claims, methods, and designs. Communicating information, evidence, and ideas can be done in multiple ways, using tables, diagrams, graphs, models, interactive displays, and equations, as well as orally in writing and through extended discussions. Teachers can help students by explicitly teaching how to read scientific texts by using applicable reading strategies. Teachers can also teach students how to read tables and graphs and expose them to scientific journals. Lastly, students need to communicate their learning through a science notebook, a display like a poster, or a presentation. You will now read an article that will give you an idea of how the practices look in the classroom and how they progress through the grade levels. Following the article, please answer the question based on this session. When that is complete, you can proceed to session 4.